next and final speaker before the drinks. It's a pleasure to welcome Daniel Ramos from Madrid, who has done a lot of work in voice comparison methods, but particularly in likelihood ratios to evaluate evidence for voice and other areas, I think. So please go ahead.
Thank you, David. Thank you very much for attending this presentation. My presentation is titled Measuring Performance of Likelihood Ratio-Based Evidence Evaluation Methods. And this is framed into a recent work that we have been conducting in collaboration to other institutions, most remarkably the Netherlands Forensic Institute, where we have tried to give some guidelines for validating likelihood ratio methods in casework. The main problem we have in this context is, all right, I'm a forensic statistician, I want to implement a method, I want to put it into casework. What is the process that has to be made in order to this method go into casework with some guarantees that it is performing properly? And properly is a very subjective term. But anyway, we didn't try to be normative in this sense. This is just a guideline of what are the minimum things that we think that should be measured or assessed. And well, this is the main motivation of measuring performance. So, and this is the guideline that we have been generated. As you can see, there are 3 authors, but there are many more contributors to these guidelines, because it has been generated after a process of discussion that started in November 2011 at the NFI, with many people at the NFI involved, many people from other institutions involved, has been being polished during the year, and it pretends to be a first version. Okay, we're trying to collect more reactions to this guideline during the years to generate better and better versions of these recommendations in order to accommodate more views of what validation should take into account of what validation should be. And we are in a slippery slope in the sense that we try to give guidelines, but we don't try to restrict too much the scope of these guidelines, in the sense that we want everyone to be able to implement this minima without being too restrictive in the people that can use it. Okay, what is this guideline about? So the objective is to determine if a likelihood ratio method is valid to be used in casework. We have developed a method to compute likelihood ratio, so we want to give the steps towards this validation. So the validation process should be documented. For transparency, of course, this is a requirement. And we would like to give some kind of standardization of this process. At this point, there is a group that is working for biometrics, automatic system computing scores from or likelihood ratios from a comparison of physical characteristics, anatomical or behavioral characteristics. And in the validation process is mainly based on empirical testing, which is kind of a common requirement that we are been hearing during all these years. And with empirical testing, data is still an issue. Many laboratories don't have data that they believe that is relevant for testing in casework. So, but our intention was not to say, okay, you must have empirical data in order to validate your system, but if you want to go into these guidelines, if you want to go into these recommendations, it is better that you start to think how to collect this data in the future. So we try to foster this data culture in this sense. That I think it is. There are relevant examples where this data culture is being going on in the forensic world, but it's not the case in many other cases in many other laboratories. So we would like to foster that culture of collecting data with this stuff. So, and as Jeff was mentioning before, it is not laboratory data that we are interested about. Of course, laboratory data is very interesting, but we will try to foster the forensic performance, the performance of the methodology that we are using to compute likelihood ratio in real forensic casework. So there are several recommendations that we do in the guideline in order to being able to achieve this in the near future. But the focus of my presentation here is not about the data. It's not about everything related to data collection or simulation or wherever. It's about the performance. So what is a good likelihood ratio method? That's the question that we were asking in the past 5 years with all these workshops and all this discussion with many people. So we try to use the ISO terminology to define several ways of measuring performance. The first time, there are the performance characteristics, what aspect of performance should be measured in the validation process. Second, the performance metrics, how to measure this characteristic that we are defining. And third, a graphical representation, then, all right, show me an illustrating plot that I can interpret, or I can see what is the performance of my method in a range of situations, in a range of possible measurement scenarios. So this is what I'm talking about here. So in the guideline, this is a table that I don't want you to read and understand right now. I will come to this later. But this is the table that we have proposed in the guideline. The important thing with this table is that it's not exclusive. It is a first attempt to give some recommendation to people that what we believe that they can measure to assess all these performance characteristics. We have been receiving feedback from different laboratories, from different groups, saying, all right, we can measure this, and we can measure this, and we can measure this. And our view is that this has to be converging in the future to advanced version of the guideline with all this is at some point integrated. But we had to give a first step in order to foster this debate, to foster these contributions. Okay, so the end of this talk is introducing a general Bayesian framework for performance assessment of likelihood ratios in the forensic field that is quite special. The second one is describe some of the performance metrics, show some examples using real forensic data, and introducing validation, well, more advertising a toolbox that we have generated in MATLAB for those who want to play a little bit with this. Okay, this is a first aim, the first objective of my presentation. So why we have defined these performance characteristics, why we understand as a goodness of a likelihood ratio method, of a likelihood ratio. So we have the general decision framework in the Bayesian context. So we have this inference from prior to posterior. We have the prior odds, the posterior odds, prosecutor hypothesis, defense hypothesis. Let's fix it to the binary case. It's easier. Then we go to the cost. That are the decision costs that we consider in our decision setup, cost or utilities. We can define it in many ways. And finally, we want to make a decision that minimizes the expected cost of our setup, right? So that defines some kind of decision rule that in a Bayesian context is based on, we compare the likelihood ratio with the priors and the costs. Of course, as a forensic examiners, forensic scientists, the guys who do the forensic evaluation, we cannot go into the prior and the costs. And if we can some kind inform the judge or jury about this, wherever they want to listen, but theoretically, we can inform the other party about these things, even though it is not our competence to make that decision. So we have to fix into this guy. Okay. So it is a question, it's finally a matter of competence. It is not only ignorance about the prior, it is not only ignorance about the cost, it is also a matter of competence. So this is our focus here. So in all this chain, what is the contribution of this likelihood ratio to the goodness of decisions? So in other words, how can we make better decisions with the LR? That will help us to understand what the LR should do to lead to better decisions, and what will help us to know whether this likelihood ratio is good or bad, which is our final performance measure that we want to achieve. Okay, better decisions are decisions that minimize decision risk, which is composed about posterior probabilities and decision costs. Okay, forensic likelihood ratio methods does not deal with prior costs, so the risk cannot be measured by a forensic statistician, by a forensic user of this method. Of course, the risk is all about expected cost based on the posteriors. So what we know is that this LR should lead to minimum cost decision, or to better decisions in that sense, minimum cost. So it can be shown that if we generate likelihood ratios that supports in a stronger way the correct hypothesis, we will arrive to better decisions in terms of cost, which is quite, let's say, well, we can say it's almost obvious to see, but it can be proved, of course. And if we see at this property as the property that we want the likelihood ratio should have, and we put it a name, we can put it accuracy, or we can put it another name if we want, but we decided accuracy because we believe that a likelihood ratio that is bigger and bigger and bigger when HP is true is more accurate, and when it's smaller, smaller, smaller when HD is true is more accurate. So we use accuracy as a definition of this behavior. So we arrive to a likelihood ratio that it's increased. If the likelihood ratio increases its accuracy, then the expected cost of decision gets better. So this is our main performance measure for a likelihood ratio. It has to be larger for HP true and smaller for HD true. Quite obvious. But it's nice to give obvious definition in order to build on it. Okay.
I'm sorry, but it's not obvious at all. Accurate means high. Accurate just means that the ratio comes from two precise numbers. But as it was pointed out, we are somehow in the situation where we are uncertain about these two numbers. So the ratio would be very low, but the two numerator denominator could be very precise, and you represent with very accuracy and low value. Sorry.
Yeah, well, it is a good point. One of the things we like is to generate discussion in this sense, because these new versions of the guidelines should accommodate also common language that we can all use. Okay. Anyway.
I think the issue here perhaps is that one would normally talk more about sensitivity or power rather than accuracy. In other words, it's the strength of the likelihood ratio in terms of the implied probability of correct decision under the two alternative hypotheses.
Okay. Okay, anyway, we get this first step. We wanted to generate this debate in the future.
Isn't that an extremely weak condition?
Sorry?
Isn't this an extremely weak condition? It just means that the likelihood ratio is not random?
I don't understand the question, sorry.
Yeah. I'm asking whether these two conditions aren't really weak in the sense that it just excludes likelihood ratios who don't mean anything.
Yeah, well, the point is that this is the definition of the performance characteristic. We want to measure it afterwards. So we can measure whether this is strong or weak depending on this value of the metric that we will define. Anyway, we can go again to this debate after. That would be okay. Anyway, so why do we like this definition? Whatever we call accuracy or anything else. Why we like this definition? First, this definition is maximum when the LR is perfect. This performance is maximum when the LR is perfect. So if the LR is infinite when HP is true, the LR is 0 when HD is true, something that is absolutely, well, it's a perfect world, but then this performance characteristic will be maximum. Okay? Maximized. This is very desirable, but probably doesn't happen too frequently. Second, this focuses on the LR and not on the posteriors or the decisions. So we can measure the accuracy of the LR, and we can, at some point, make this measurement independent on the prior and the cost. This is quite priority in forensic field, because prior and the cost are unknown or not a competence at all. Or finally, this addresses the ultimate aim of the likelihood ratio. So it's aiding finally to make better decisions. If we increase this performance characteristic, if we make it better, this performance characteristic, we will lead to better decisions in our aiding to the bad factors. So that's why we think that this primary measure makes sense. Okay, so how can we measure this? And it comes to the question, one of the questions before. So, as defined, the performance characteristic is something that it has not a value of performance, so we want to measure right now. So we came to the use of strictly proper scoring rules because they have many properties. Some of them we will introduce here. But well, I like it, especially this paper. I think it's quite revealing for me. The strictly proper scoring rule. There are many more statistical literature. But what is a strictly proper scoring rule? It's a rule that assigns a penalty to a posterior probability, depending on what we think is good or bad posterior probability. It has properties. Its average value fosters some kind of behavior on the posterior probability and so on. But this is an example, strictly proper scoring rule, contextualized to this forensic posterior probability context. So if we have a posterior probability of prosecution hypothesis given evidence, and HP is true, the penalty should be high, very high, when this probability tends to 0, and should be low when this probability tends to 1. And this is the opposite. We know that HD is true, so the penalty should be low when this probability tends to 0. Should be high when this probability tends to 1.
What probability is on the horizontal scale on the right?
This is the probability of yeah, it is flipped. It is.
Sorry, which one is it?
Yeah.
Yes, which one is it?
This is probability of prosecution hypothesis, and this is probability of prosecution hypothesis. Sorry, it is changed.
Prosecution.
Yeah, prosecution.
So in both cases, it's the same.
Yeah. In both cases, it's the same. Sorry, it is a mistake of mine. Okay, thanks. Okay, so we have this posterior probability. We can assess a set of these posterior probabilities. Finally, we cannot compute these posterior probabilities being a forensic scientist. So I am a forensic scientist. I am in the laboratory. I want to see if my method performs good or bad. I generate a validation set with a lot of cases. I compute likelihood ratios. But with likelihood ratios, I cannot go and assess the goodness of my posteriors with a strictly proper scoring rule because I have not a posterior. I have a likelihood ratio. So our proposal is to first give a representation of what would happen for any prior and decision costs if we assess the goodness of those posteriors for a wide range of priors. That's the proposal of the guideline. So we set up a validation experiment. We compute likelihood ratio values with a big database. We know the identities. Some are same source comparisons, some are different source comparison. In some comparisons, HP is true, some comparisons, HD is true. Then we do this for validation, not for casework, just for validation. Then we simulate this experiment in laboratory. And we know the ground truth. We have a set of true HP LRs, we have a set of true HG LRs. And we compute this empirical validation likelihood ratio set, let's call it like that. So we have these histograms for the logarithm of the likelihood ratios. Hopefully this separation is small. Well, this separation is big, this overlapping is small. And finally, we vary the prior and the costs, compute posteriors with all these possible priors and costs, and do a representation of this strictly proper scoring rule, the average value on all the validation, on all the validation set for all possible priors and costs. So we vary these magnitudes. So what we do is, in these simulated experiments, if we assume some prior and some costs varying in a range, what would be the accuracy of likelihood ratios as a function of these priors or costs? So we do a representation as a function of the priors. That's what we propose. So we don't set the prior at all in a validation experiment. We don't fix the given prior in a validation experiment. We just see the behavior of this as a function of the prior. This leads to the average of a strictly proper scoring rule over a set of posteriors that have been computed for a wide range of priors. So we change it. And we have proposed one of these average values of strictly proper scoring rule. It's called empirical cross entropy. It is known in many fields related to pattern recognition. And it's a weighted average, in fact, because it is averaged by the priors. And this empirical cross entropy can be represented in graphs like that. So we vary the prior odds, we move along the prior odds axis, and we see what is the average value of the strictly proper scoring rule that we would obtain with these likelihood ratios and the prior in the x-axis. So in some sense, there is a variation of the prior odds to see what would happen if we use this statistical method with a given establishment of the prior odds. So we only vary the prior odds in the validation experiment and not in casework. Of course, as usual, this is something that has generated some fear in the past. No, we're not saying to fix the prior odds to a value. We're saying just vary the range of prior odds so you can see what would happen if you would have some particular prior odds in a case. So, why strictly proper scoring rules? Strictly proper scoring rules is one way of measure this behavior of the likelihood ratio. It's better as it is bigger when it supports the correct hypothesis. HP hypothesis, or lower if it supports the correct HC hypothesis. But why strictly proper scoring rules? Well, it's strictly proper scoring rules allow to measure this magnitude, this property of likelihood of posterior probabilities that is extremely important, and well, has been studied in the past very intensely. We have two relevant contributions here, and in this contribution in particular, it has been stated that this strictly proper scoring rule can be decomposed into calibration and refinement, under some conditions. So, and more recently, particularly in this contribution, it has been there have been generated algorithmic methods in order to do this decomposition explicit, with some particular examples of strictly proper scoring rule, particularly this empirical cosentropy rule. So at the end of the day, we have this basic measure that is, okay, we have the average value of a strictly proper scoring rule, and we can decompose this into two magnitudes. One magnitude related to the discriminating power of the likelihood ratios, understood of this, how these likelihood ratios are really separated between HP cases and HC cases. So how these likelihood ratios are able to distinguish between the two propositions. And you can decompose this into this discriminating power and the calibration of likelihood ratios. Calibration means that, well, if I use these likelihood ratios to compute a posterior and make decision with this, I will obtain better decisions if I obtain better calibrated posteriors. So this calibration of likelihood ratios means that these likelihood ratios obtain calibrated posteriors, in the sense of calibration has been studied in the past. This decomposition is important because it allows to distinguish between two things that might happen with my model. Either my model is not able to distinguish between things under the two hypotheses, so either my model cannot in some way is not able to extract discriminating information. This is condensed in this particular part of this strictly proper scoring rule average. But if my method is not representing probabilistically my features in a correct way, let's say, then this calibration will suffer. So in some way, it allows to identify the source of a problem. So if probabilistic models are in some way senseful with respect to the data, then this calibration would get better. But if the models extract more discriminating information, then discrimination will get better. So all in all the strictly proper scoring rule will be better if we improve one of these two quantities. So following these ideas, there are some metrics that has been proposed in the guideline, and there are some metrics that have been proposed by us, by other people to us, to be included in the guideline in the future. One thing that, of course, we will take into account. These are the metrics included in the guideline. These are the graphical representations included in the guideline. They are split into two, different kind of performance characteristics. There are primary characteristics and so-called secondary characteristics. The primary ones are these three characteristics that we have been discussing before. The accuracy as a global definition of what is the behavior of the likelihood ratio with respect to decisions, and the discriminating power as what is the ability of likelihood ratios to extract discriminating information to distinguish between two different propositions, and the calibration as the reliability, probabilistically talking about this likelihood ratios, and different metrics and representation that we'll talk about very briefly. And secondary measures talk about the behavior of these primary measures. So for instance, if I decrease the quality of my samples, does my performance decrease a lot or not? So we're talking about robustness. There's a paper recently from the NFI where they analyze what is the somehow variability of the models with data sparsity, and this can be viewed as a robustness measure to data sparsity. Coherence is one of secondary measures that says, all right, if I include more informative features, is my model able to extract this information to give better likelihood ratios? So if it happens, then my model is coherent in that sense of performance. And generalization is all about my model works very nice if I trained it with known data. What happens if the data is not known? What happens when I work in predictive mode? And what happens if I work with unseen data? So that's my performance is degraded or not. Again, this primary and this secondary are proposals. Of course, the secondary can be extended enormously. But we believe the primary, it's a well description of what we understand as a good likelihood ratio. But these ones take into account all the possible sources of variability that might happen in forensic context. Okay, we can have data sparsity, degraded quality. We might have a strong mismatch in the conditions, and so on and so on. Okay, this is one measure of discrimination. It's called dead plots. It's a special type of ROC curves. We like them in speaker recognition field because these axes are Gaussianized. So the ROC curve becomes a straight line when you have Gaussian distributions, which is interesting. And we have also, in some way, a representation that when you go to very, very low rates of error, it becomes visible still. So it has this visualization property. We have a summarizing metric that is the equivalent rate. It can be a measure of discriminating power. But it's not a measure of calibration. You cannot measure calibration with ROC curves, with dead curves. So in some way, with respect to what it has to be measured in the likelihood ratio, it's incomplete. We have also tippet plots that have been very popular in the forensic literature in the past. And well, we can see many of these things in the tippet plots. The calibration is related to in some way to how these curves are centered around 0. The discrimination is related to the separation of these curves. You have summarizing measures in the forms of rates of misleading evidence here and here. But our warning is that tippet plots do not measure them explicitly. So you have to in some way to do some kind of interpretation of what tippet plot is doing, is showing. In some way, these we have included it in the guideline because they are extremely popular, but not because they are the best way that we think that performance should be measured. Finally, you have these empirical cross-entropy plots that we have been proposing in the past. It is one way of measuring the goodness of the likelihood ratio as a whole. You have the red curve is what we have called the accuracy for given priors, for different priors. And the discrimination is the dashed blue curve for different range of priors. And also the difference, of course, is the calibration. So if these two curves are very close together, then the calibration is better for a given set of likelihood ratios. And it has a summarizing metric that it's called CLLR, that it is currently proposed before ECE plots have been proposed because it has properties related to the average cost of decision. So finally, the decision framework is aimed at reducing the average cost. So CLLR is kind of average of this cost for a wide range of priors and so on. Anyway, this is all summarized here. I don't want to go deeper into. My time is running out also. More performance metrics and representation that are not included in the guideline, but we think that we will be including the next version of the guideline that we are generating in the future, in the near future. First one are these so-called normalized Bayes error plots. It's again, the idea is to move the prior odds into an x-axis to see what is the error, what is the normalized Bayes error that we obtain. The Bayes error is normalized for better visualization, and also it is related to CLLR, but it's not related by one point of the curve, as here, but by integration. There is a way of integrating these curves that leads to CLLR. So in some way, there's also a relationship as a summarizing metric. And finally, it has been proposed, this can be found in several publications, most remarkably publication from Irving Good in the past, that, okay, the expected value of the likelihood ratio under one of the propositions should be 1 if the calibration is good. So in some way, this deviation from this value of 1 can be a measure of this miscalibration in some sense. This both has been proposed by us. We're probably including it in the future version. So a brief example of what we do here. So we have recently proposed something in the evaluation of glass evidence. This is a paper of us and +1 and people in my laboratory. So we have a setup of glass chemical profile comparison, and we compare two models. First one is a classical model for continuous data from Aiken and Lucy that most of us here know. And the other one is a proposal to replace the KDF for the between source distribution with the Gaussian mixture model that is trained on data. The reason for doing this is that this model proposed KDF for the between source distribution, but KDF, when the dimensionality gets higher, the covariance matrix for the kernels, it's a little bit mismatching with respect to the data that we are handling. So we observe this effect. We try to provide a better fit of the between source for using a Gaussian mixture model that works a little bit better with some under this scenario. So and this is what I wanted to show you basically. So we do the validation using forensic profiles that can be found. They are publicly available in one book that we have recently written with the people at Krakow and University of Edinburgh. And if you use that data to do the experiment of performance, you see in this case, for example, these are car paints. You can see that with KDF between source distribution, the average value of the strictly proper scoring rule is much higher than in the case of GMM between source modeling. So in some sense, we can say that for a wide range of prior, it works better with the GMM rather than a KDF. This is in some way a way of checking whether our models are doing what they're supposed to do. Okay, finally, I would like to advertise this. This is, well, the slides will be public for everyone. This is we have called it validation toolbox. Probably it's not a validation toolbox, but a performance measuring toolbox. It is aimed at forensic practitioners that are not going into the deep of the R and MATLAB packages for measuring performance. It has a GUI, the graphical user interface. It's an easy way to measure likelihood ratio performance. It's documented. We are planning to do an article on that and so on. So we want to use this for validation, or even though play a bit with your data, then it's available. Well, as conclusions, very briefly, we have proposed a guideline for validation. It is based on empirical testing and performance measurement. We want to extend it in the future, so all comments are welcome. And we have defined the performance of likelihood ratio values in a forensic context. We try to get out of the definition of prior and costs, because we are talking about forensic setup. And the likelihood ratio aids in the decision process is the driving idea that allow us to measure the performance of likelihood ratios with strictly proper scoring rules. We have stressed the importance of calibration for likelihood ratios. I think calibration is one of the things that in some way can control what we do with likelihood ratios when we compute them and we do an empirical test. I think the calibration is one of the most important things we can measure. And finally, There is a plethora of performance representation and metrics. We have proposed some of them. We are open to include more in the future, and this is a continuous improvement that probably will lead to more and more versions of the guideline in the future. So thank you very much for your attention.
Okay, thank you very much. You have left us some time for questions, so let's see if my promise that there will be questions is right. I see one already. Yeah, James.
So Daniel, just technical question. A mixture model and a kernel density estimate. Kernel density estimate is just a special case of a mixture model. So I'm not sure what you're distinguishing between those two things.
Yeah, the point is that is the way on which the covariance matrix of the kernel is computed. So if you go into Colin and David's model, they take the whole data and they compute the full covariance matrix for all the whole data, and then they reduce it, they scale it for the kernels. That is nice. When the dimension is low, it can work. As long as you go more high dimension, then locally you have many difficulties. So with a GMM, what you do is to try to train the model locally to stick the covariance matrices more to the local data. So that's what overcomes in that way.
Could I ask more about the basis of the work? You said you looked at glass and you've put the data from 2 databases and then tested them. Did I hear that right?
Well, we take a database of chemical profiles. It is, I'm not a chemist, but scanning electron microscope with...
Microprobe.
Yeah, that's it.
Yeah, but, and you just looked at 2 populations of data from 2 databases?
No, it's just one population. And the population is used as a cross-validation in order to train the model and test the model using different
So
data.
have you actually tested it against unknowns? So you have an unknown glass sample.
Yeah. It is done by cross-validation. So you use part of the model to train the parameters, and then the rest of part of the database to train the parameters, and then the rest of the database to test models. So it's not a different database, but you split the database into pieces, and then you take one piece for testing, one piece for background training.
Oh, I see.
And you repeat that process.
So what do you do when you can't have a proper database? For example, soil. People say there are databases of soils, and there are not.
Yeah, well, of course, you cannot do empirical tests if you don't have empirical data. That's something. So.
No, but they claim to have empirical data because they will take a range of samples, and then they will test that against an unknown. But the basic premise is flawed. I've seen this. Basic premise is flawed because they assume homogeneity where there is none. So what do you do then? What I'm worried about is you've got the strictly proper scoring rules. What about the strictly proper sampling rules? I mean, that's important too. And that's the whole thing about this. I'm not questioning the mathematics, but I'm very worried about where you start. And you said you have to rely on the competence of the forensic scientist. That's basic to the whole methodology.
The point is that one of the things that we are proposing is that we measure in some way also the variability of the measurement procedure depending on data sparsity. Of course, if it's a given database, we have to take into account some variability on what we measure. That's the point. That's exactly in the direction of this publication that I was mentioning before about this forensic statistician from the NFI. They say, all right, we have data sparsity set up, and we show that, and they show that there is variation in the performance measure depending on exactly what is the operation point that we are setting the priors in order to in some way take into account that probably our validation methodology given to a sparse database, for example, with sampling variability, it is not so, in some sense, reliable as it should be. So this is something that has to be done, definitely. Yeah.
So you're going to test the whole of as many soils as possible in Holland to get a database to test this model if NFI is going to do soil testing using this technology.
But I'm not sure about the question.
Oh, no. Perhaps I can talk to you later about it.
Okay, yeah. But if you mean that we go and you validate your method for the possible sources that you have in the world, of course, we cannot achieve that. But with this empirical data, what you can in some way estimate is what is the variability of your performance measure due to this data
I understand.
sparsity. I mean.
Yeah, I do understand, yeah. But I'm a bit worried about the beginning part.
Okay, we can discuss it.
No.
Okay.
I have a couple of questions. One is political, let's say, because I don't know your community. So who gives you the authority to write these guidelines, which should be a kind of, no, it's a guideline that the people should somehow follow?
Well, there's no...
Where does it come from?
It's a set of recommendations. There is no authority that says, okay, we must follow this guideline. In fact, there is discussion about this guideline. It reflects the views of some part of the community that we have been in some way asking for recommendations by a discussion process that took years. But there's not some commit on that.
And then the second one is more technical about you said the expected value of this ratio, what I call the base factor, should be 1. Why? Usually, pieces of evidence are not taken at random. Usually, they are taken because they provide some support. So you don't expect that in real life they have expected value of 1.
Well, in fact, if you go and compute many likelihood ratios over different data sets, one way of and somehow test whether these likelihood ratios present good calibration is to achieve that the expected value is 1. This has something to do with the idea that if you have, for example, a model that computes likelihood ratios, and your likelihood ratios are a lot of discriminating, you obtain big likelihood ratios in general. Probably your likelihood ratios that point in the wrong direction will also be big. So on average, given one given hypothesis, you will probably obtain an average of 1 if the calibration is good. So as far as I know, because this paper was recommended to us, as far as I know, there's a proof for this.
It's a completely trivial thing.
Yeah.
The likelihood ratio is the ratio of two probability densities, P over Q, and you multiply them by Q and you integrate, you get 1.
That's it.
So if your likelihood ratio really is a likelihood ratio, this will be true.
That's it. So that's related with calibration. So if the likelihood ratio really as a likelihood ratio will present good calibration.
I mean, in real life, when you calculate this, because it matters in a trial. Okay. Then in a trial, pieces of evidence are brought because they have very high ratios. And they do not come at random.
Yeah, but I mean, that is probably in casework. But when you do a validation experiment, you probably have to stick to a wider scope, not only the comparisons that would go to casework, but every comparison that the model has to cope with. I mean, so probably it's more related to what you say, it's taken at random. So in a casework, of course, there will be a lot of circumstances that would make this not to be taken at random. But when you do the validation, the performance measuring in your laboratory in forensic situation, you have to, at some point, cover a wider range of possible comparisons that can be obtained. I'm not sure if you're referring to that, but I think it's going that direction.
One more question there.
Yeah. So do you have any recommendations about when the validation is good enough? Do you have any threshold for the CLR value or any recommendations about when a plot looks good enough?
Well, our view is that there's not such a threshold in general. I mean, you go to the laboratory, you measure your performance, you obtain some rates, wherever you obtain, whatever performance measure you use. The moment in which this performance measure are good enough, it is nothing that can be set externally as a rule that says, there are some restrictions. For example, this empirical cross entropy cannot be bigger than 1, because if it's bigger than 1, it will be worse than tossing a coin. So let's go home with this method. Okay, but in order to in a laboratory to decide when to start using this in casework, this is something that the guidelines shouldn't recommend in any way, because it depends on many policies internal to the laboratory, and also we think theoretically there's not an answer for that. Because, okay, you go and say, all right, the equal error rate, when is good enough? 10%, 5%, 1%? I don't think there is an answer for that. So each laboratory should define transparently their, in some way, policies to when decide that something has to be taken into casework. And I think it happens like that, you know, when DNA comparison method is good enough to go into casework. So it depends on the situation, it depends on many things, but at some point the laboratory says, okay, this is good enough to go into casework, but I don't think we should give that recommendation in some way because there is no theoretical basis for that.
Okay, we'll finish there. Thank you very much, Ben.